most of the mass and all of the positive charges are concentrated at the very center, and that particular portion is known as a nuclei. If you have hydrogen, then you have 1H1, where the mass number and atomic number are simply the same. So protons plus neutron will give you the mass number. So here it is 1 plus 2, which means there are 2 neutrons here. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And here we are going to start a new chapter, that is nuclei. So we learned the intricacies of the atom. Now we are diving deep into the world of the nuclei. So let's see what nuclei holds for us. So again, this will be mostly based on whatever you have learned in your chemistry chapters. Again, there is nothing new we are going to learn today, but still, for the sake of physics, we have to learn it. So already you have seen what atomic number is, what mass number is. All this you already know from your first PUC. But again, let's just refresh that. To start from, we'll start with what exactly is a nucleus. So we do know that a nucleus, or the plural form of nucleus, is nuclei. So again, so what are nuclei? Nuclei are just all the positive charges densely packed at the very center of an atom. So we can say that a nucleus is nothing but all the positive charges and most of the mass concentrated at the very center of an atom. So if this is an atom, then we can say that most of the mass and all of the positive charges are concentrated at the very center, and that particular portion is known as a nuclei. And one more important thing is that the volume, that is the volume of the nuclei, or the volume of the nucleus is actually 10 raised to minus 12 times the volume of an atom. But then again, you already know about all these funny little details because you have already learned this in your first PUC. You know what an atom is, you know what an electron is, you know what a nucleus is, and what the nucleus actually holds. All of these things you already know. But still, we are just going to refresh a few things and we are going to jump forward this particular chapter. So, what exactly is atomic number and mass number? If we can represent any element, may this be He or Na or any other element on the periodic table, we can represent any element that is having an atomic number and mass number just like this, being this will be the atomic number and this will be the mass number. So any element can be represented like this. For example, if you have hydrogen, then you have 1H1, where the mass number and atomic number are simply the same. For example, you have hydrogen with atomic number 1 and mass number 2. So you have atomic number 1 and mass number 2. That is, if it is having 1 proton and 1 neutron, then again its mass number will be 2, and atomic number, since it is only having 1 proton, it will be 1. Just like that, you can represent any element like in this particular format, where the X is symbolizing the element, the Z is symbolizing the atomic number, and the A is symbolizing the mass number. So again, so what is atomic number and mass number? Again, already you know all this, but just for my sakes, I'm just going to define these particular terms. So again, atomic number is simply the number of protons in an atom. So don't mistake it for the electrons. In most atoms which are electrically neutral, the number of electrons and the number of protons will be same. That is why we mistake it. That is, we mistake the atomic number sometimes for the number of electrons. But in actual case, it is actually the number of protons in an atom, or simply in a nucleus. And what is mass number? Mass number is the total number of nucleons. total number of nucleons, or simply protons plus neutrons. Whatever the number of protons and number of neutrons are there inside the nucleus, then we can say that P plus N, or simply number of protons plus number of neutrons, will give you the mass number. So again, if there is one proton and one neutron, then the mass number will be 2, but the atomic number will only be 1. So that is how you can define atomic number and mass number. So for example, if I ask you what is the number of neutrons in this particular atom, you can simply say that, okay, I know that atomic number is actually equal to 13, which means there are 13 protons in this particular atom. And then, okay, the mass number is actually 20, which means it is 13p plus, I don't know how many number of neutrons, will be equal to 20. That is the mass number, which means that 20 minus 13 will give you the number of neutrons, and the number of neutrons will be 20 minus 13, that is 7 neutrons will be inside this particular atom. So like this, you can actually find out what is the number of neutrons, what is the number of protons inside an atom by just looking at the atomic and mass number. So again, but sometimes atoms can actually trick us, because the same element might have different characteristics or different twins or different siblings, we can say, because the same carbon atom will have different siblings. The same hydrogen atom will have different siblings. Like there can be hydrogen 1H1, there can be hydrogen which is having 1H2, or maybe there is even a hydrogen that is having 1H3. We don't know. Is it possible? Is it not possible? Again, you already know that this is still possible. So depending on the number of protons or neutrons that are residing inside a nucleus, we can actually categorize these particular atoms. So how do we exactly do that? So further, we can say that these can be categorized into 3 different categories, that is mainly isotopes, isotones and isobars. So what exactly are isotopes, isobars and isotones? So what exactly are isotopes? So isotopes are basically the same element which is having different mass numbers, or simply we can say that they are elements which is having atomic number the same, that is atomic number will remain the same, which means the element is not changing. The atomic numbers are still the same, but the mass number is actually a different number. For example, we can say that the number of neutrons inside that particular atom is different. So that is why we can say that the element will remain the same, but the mass number will be different. For example, we have carbon which is having carbon 12 and carbon which is having carbon 14. So both of these are very different in their own characteristics. So one can actually be used for carbon dating, that is determining how old fossils actually are. Both will have different uses based on what their mass number actually is. For example, carbon 14 and carbon 12 is a very clear example of how their uses actually differ based on their change in mass number. But for you, only thing you have to remember is that isotopes are elements which are having same atomic number but different mass number. And similarly, we also have isobars and isotones. So what exactly are isobars? Well, that's also very simple. That is, isobars are elements which are having same mass number but different atomic number, which means the element will be different but their mass numbers will be the same. For example, here you have tritium, and again their mass number is same, that is 3, and here you have helium which is having a mass number of 3. Just like that, you have carbon which is having carbon 14, that is mass number 14, and similarly nitrogen also which is having a mass number that is of 14. So elements which is having same mass number but different atomic number is known as isobars. And again, the last thing is isotones. You have already guessed it, which is having same number of neutrons. So again, isotones are elements which is having same number of neutrons. So we can just say that the examples will be hydrogen, which is having a mass number of 3 and atomic number of 1, and helium, which is having a mass number of 4 and atomic number of 2. Again, you can easily find what is the number of neutrons here, because proton number is 1. So protons plus neutron will give you the mass number. So here it is 1 plus 2, which means there are 2 neutrons here, and here also it is 2 plus 2, which means here also there is 2 neutrons. So if the neutron numbers are same for different elements, then we can say that okay, they are called as isotones. So we studied about what is isobars, isotones and isotopes. So what is so special about nuclear size and nuclear density? We already know that as we go down the periodic table, the atoms actually increase in size, which means that they're actually related to their radiuses. That is, the atomic number is actually related to the radiuses, because as we move down the atomic scale, that is, as we move down the periodic table, the size of the atoms actually increase. As we can take an example of hydrogen and helium, or simply hydrogen and xenon. As you can see that as we move along the periodic table, the size of the atom actually increases. Or simply we can just say that atomic number is actually proportional to their radius. But how is it proportional? It is actually proportional to 1/3, or simply the cubic root of this particular quantity. Or we can just say that atomic number raised to 1/3 is actually proportional to radius of the atom. Or much more clearly, we can say that atomic mass number is actually proportional to the radius of any atom. And to avoid the proportionality sign, we can just introduce a constant of proportionality, which just states that a raised to 1/3 r naught will be equal to r. Or much more neatly, we can write it down as r is equal to a raised to 1/3 r naught. So this relation will give you the relation between the radius of an atom and its atomic mass number. And the value, that is the constant r naught, will be having a value of 1.2 into 10 raised to minus 15. So again, r naught is a constant and r naught will be having a value of 1.2 into 10 raised to minus 15 meters. So this will actually give you, or this is a formula which you can use in order to find out what is the radius of any particular atom if you know the atomic mass number of that particular atom. Now we talked about what will be the radius of an atom, but there is still one quantity remaining, that is density. So how do you find density? But just before that, we need to know what is the volume of that particular atom, right? Let's assume, again, we are going to assume that that entire atom is supposedly a sphere. So if that is a sphere, then we can say that the volume of a sphere is given by the equation 4/3 pi r cube. And again, here r is the radius of the particular atom which you are taking. So here again, you have an equation for the radius of the atom, that is a raised to 1/3 times r naught, or simply you can say that it will be equal to 4/3 pi. Instead of r, we can write it as a raised to 1/3 r naught cube, or simply you can say that this will be equal to 4/3 pi, 1/3 and 3 will cut off, and here there will be a cube, which means that 4/3 pi a into r naught cube. So here you can see that 4/3 is a constant, pi is a constant, and r naught cube is also a constant. So we can just take them all together and say that okay, volume will be equal to 4/3 pi r naught cube a. So which means that volume is directly proportional to the atomic mass number again, or simply we can say that V is also directly proportional to A. So you know that R is now directly proportional to A raised to 1/3, but here in this particular case, that is volume is actually directly proportional to the atomic mass number. If you increase your atomic mass number, the volume will also increase. If you decrease your atomic mass number, the volume will also decrease. Again, we are not done. We have to still find what is density. So how do we find density? Again, we know the equation for density. Density is nothing but density rho is equal to mass divided by volume. So we have the equation, we have the quantities, we just need to calculate the result. So how do we calculate the result? So rho is equal to mass divided by volume. And again, here mass is nothing but atomic number times, atomic mass number times the unified atomic mass. So again, unified atomic mass, previously denoted as AU, now denoted just as U, that is unified mass, is what we are going to multiply with. So again, it is just a scale of reference. For example, if you have 5 kgs, you multiply the scalar quantity, which is 5, with the unit, which is kilograms. So you'll get 5 kilograms. Just like that, we have the unit, which is U, unified mass unit. Earlier, it was known as atomic mass unit, AMU or AU. Now it is just being called as U. So you have the atomic mass number as A. If you multiply that with U, you will get your net mass of that particular atom and divided by the volume which we already found out. So 8 times U divided by 4 by 3 pi R0 cube into A. So if you do this, you know that A and A will cancel each other out. Then you have U by 4 by 3 pi R0 cube. So we can actually calculate this particular result. So it will be actually equal to, so unified atomic mass is actually 1.67 into 10 raised to minus 27 divided by 4 by 3 into 3.14 into R0 cube. So R0 will be having a value of 1.2 into 10 to the power minus 15 all cube. So again, the interesting fact here you have to realize or observe here is that the density of any particular atom, for that matters, is actually independent of their atomic mass numbers, or simply independent of any other quantities than the constants that are present here today, which means the density of most of the atoms is actually easily calculatable to a constant value. So again, that particular result will be equal to 2.3 into 10 raised to 17 kilograms per meter cube. This particular quantity is actually a constant value. Now that is mind-blowing. Even if you take the most biggest atom you can find and the most smallest atom you can find, the densities are relatively the same. Now that is an interesting concept in terms of atoms. So at this particular result, you can see that density of all the atoms are now a constant value. Now that is mind-blowing. Even if you take hydrogen, which is a very small atom, and if you take neon, a comparatively larger atom, and if you take any other atoms in between also, it does not matter. All of their densities will be equal to 2.3 into 10 raised to 17 kilograms per meter cube. Now that is very astounding. Now, let's leave all the chemistry behind and let's learn about some physics which you are actually seeing for the first time. So let's dive deep into the physics. But just before you study what exactly is mass defect, you need to understand a famous equation that changed the entire scape, or simply the fabric of reality itself. That particular equation is E is equal to mc squared. The famous equation that is laid out by Sir Einstein, which stated that energy is actually directly proportional to mass, or simply introducing a constant, which is the constant, that is the velocity of light squared is the constant that is introduced in this particular equation. Together they are known as energy mass equivalency principle. That is, energy is being equated to mass, which means mass can actually be converted into energy, and energy can actually be converted into mass. So what exactly happens? If you have any particular mass, okay, let's say this particular pen. If this particular pen or marker is accelerating. Let's say it is increasing its speed to a point where this particular pen is now accelerating and accelerating, and it achieved a speed which is equal to the speed of light. Theoretically, you cannot achieve any object which is below the speed limit, that is below light speed, cannot achieve light speed. But let's say you are achieving that particular speed. Then the entire quantity, that is this particular quantity which is having a mass of m, that particular mass will be converted into pure energy. And let's say that any quantity, let's say for a photon is moving at light speed, right? If that particular photon is now slowing down, its energy will be converted back into mass. So this particular relevation, that is energy and mass are equatable. They are interrelated. Energy can be converted into mass. Mass can be converted into energy. This particular finding is very, very, very important. It was the start of a very new realm for which he didn't even know he opened the doors to. Again, from this, the photoelectric effect and this particular equation, he's famously known for his special theory of relativity, E is equal to mc square, and the photoelectric effect, that is E is equal to h mu. And these are very groundbreaking theories in the world of physics. So why did I just tell you about what Einstein's equations was, and why is it so relevant? So Einstein just said that energy and mass are just interrelated, or simply mass is another form of energy. So if mass is another form of energy, it cannot be destroyed. It can only be converted into certain other forms, right? So the point here is that if I take, let's say I took 3 neutrons or 3 protons like this. Okay, these are 3 protons and I'm also taking 3 neutrons, which means that I can exactly weigh how much these protons and neutrons are. So I know what is the weight of a proton, I know what is the weight of a neutron. Let's say that I added all these together and I'm getting 10 kilograms. Okay, I'm getting 10 kilograms. Just roughly, just think that if I took individual protons and neutrons and I measured them and I'm getting 10 kilograms. Now, using these particular protons and neutrons, I created a nucleus. The same number of protons and neutrons are inside this particular nucleus also. But when I measured the mass of this particular nucleus, where it should be 10 kilograms again, because the same number is inside this particular nucleus, there was seen that it was only 9.8 kilograms. There was additional mass which was missing. So where did the mass go? That particular problem is known as mass defect. That is, when you take individually the nucleons and if you measure them, they will have a certain amount of mass. But when you take that same elements and make a nucleus, some of the mass was actually missing. So where did this mass go? That particular explanation or that particular phenomena or that particular issue was known as the mass defect problem. So where did that mass actually go? So that is where the famous E is equal to mc square equation comes into play, because that particular mass was actually converted to energy when the nucleus was actually forming. So again, we can define the missing mass, or simply we can say that the mass defect can be explained as the difference in masses of the free nucleons. That is, when the nucleons, that is protons and neutrons, when they are kept freely at their static states, that particular mass and the mass of the nucleus, that is when all of these nucleons are used in order to produce a nucleus. If I take the difference of mass between them, then the missing mass is actually known as the mass defect, which is indicated by delta M. So how you can actually find them is mass of the protons times the atomic number plus mass of the neutrons times the neutron number. So A minus Z just means that the atomic mass number minus the atomic number, which will just give you the number of neutrons. So again, MP is the mass of the proton, Z is the atomic number. It is not plus, it is actually MP times Z, not plus. There is no plus sign here. it is MP times Z, which will give you the mass of the protons, and here it will be the mass of the neutrons. Simply we can say that it is the mass of the nucleons in this particular side, and here it is the mass of the nucleus itself. That particular difference will give you the missing mass, which is known as mass defect. Now we have to study about something that is very important in the entire universe, that is known as the binding energy curve. But before understanding what is binding energy curve, you have to understand what is binding energy. You have already studied this in your PU first year in your chemistry syllabus and in your physics syllabus. The only difference is that in physics you studied binding energy in terms of gravitational potential energy. Here, in strictly speaking, in terms of nucleus, what exactly is a binding energy, or what is binding energy defined as? So, imagine that you have a big nucleus or a small nucleus. Doesn't matter. If you have a nucleus, that is enough. So, imagine that you have a nucleus and you have all these nucleons inside this particular nucleus. That is, you have neutrons and protons. So, if I want to remove this particular neutron out of this particular nucleus, then I have to do some work, which means I have to spend some energy in order to pull this particular nucleon out of the nucleus, because they will be strong nuclear force which are keeping these neutrons and protons inside the nucleus. So, if I'm trying to rip one out, I have to give sufficient energy. So, the minimum energy required in order to remove a particular nucleon from the nucleus is known as binding energy. Or simply we can say that binding energy binds all the nucleons inside a nucleus. So, in order to take one out, we have to give at least an energy which is equal to the binding energy or more in order to take out that particular nucleon. So, we can define binding energy as the minimum energy that is required in order to free a bound nucleon from the nucleus. And that particular binding energy, can be found out through a simple equation, that is delta mc square. And again, delta m is the mass defect, that is the missing mass, and c square is a constant again, which is nothing but the velocity of light squared. Again, this will be very similar because you have already seen the equation. E is equal to mc square. It is almost the same equation, just talking about the missing mass and the energy which is holding a nucleon. So again, this particular quantity, that is binding energy, will be equal to delta mc square. That much energy you have to spend in order to free one nucleon from the nucleus. Now, coming back to the graph, that is binding energy curve. So, what is this binding energy curve? Before that, we have to understand just one more quantity, that is binding energy per nucleon. That is simply binding energy per nucleon, just means that binding energy divided by its atomic number of the given nucleus. Atomic mass number of the given nucleus. So again, if you divide the binding energy by the mass number or simply atomic mass number of the given nucleus, you will have what is the binding energy per nucleon. So what is this binding energy per nucleon? It means that how much energy you need in order to just pull out one nucleon from the nucleus. So how much energy does it take? So that particular value is graphically represented here, and this particular graph will give you how much energy you actually need in order to pull out one nucleon or one particular nucleon, that is binding energy per nucleon for various atoms or simply various elements. And here the energy is denoted in terms of mega electron volts or simply MeV. Again, here EB just means that it is the binding energy, and by A means that it is binding energy per nucleon, or simply we can say that this EB by A will give you what is the binding energy per nucleon. And again, here it is the mass number. As you can see that we are starting from the lowest element that there is, and then we are slowly moving up. As we move up, you can see that the nature of the graph just suddenly dips like this for some time. That is, here for helium it is quite a high value, but for lithium it is quite a low value. So why is that particular difference there? Again, the difference is there because here helium is much more stabler element, while lithium is comparatively a less stable element. Same is the case for beryllium and boron. Same is the case for carbon and nitrogen. Like that, as we move up, some elements will be completely filled, right? Some elements, that is the outermost shell, will be half filled or completely filled, which means that particular atom will be more stable, which means we have to provide even more energy in order to get one nucleon out, because if they lose that one nucleon, they will become unstable. In order to prevent that, the atom will do, or the nucleus will do everything in its power not to lose that one particular nucleon. So for that reason, the stabler nuclei will be hesitant in order to give that particular nucleon, which means the binding energy per nucleon will be higher for stabler elements. If it is less stable, then obviously the energy requirement will be lower, because they are ready to give away that particular one nucleon if they can attain stability. As you can see here that after all these values, there is one particular value which is the maximum value in this particular graph. That particular maximum value is attained by the element that is iron. Iron will be having the highest binding energy per nucleon in this entire universe. After that, you can see that the curve is actually dipping, which means that after this element, the binding energy requirement is also decreasing. But up to this element also, it is increasing. Iron is the point where you will have maximum binding energy per nucleon, which means that iron is the most stablest nucleus that is existing in this particular universe. So I just wanted to show you the graph today. What are its observations and what are the conclusions will be discussed in the next session. Until then, I'll see you all. Thank you.